Welcome, crew. In this unit, I guess this last half of a unit and the next unit, we're going to finish up our trig identities, and then we're going to look at how to use trig to solve triangles. So we'll get to that later. Today we're going to look at two more sets of identities. That would be our cofunction identities and our even and odd identities. So let's dive in, and we're going to start with our cofunction identities. So consider this right triangle where we have our right angle, and then we have our two acute angles. One we're going to call alpha, that's its measure, and the other one beta. And then we have the three sides of the triangle, right? A opposite alpha, B opposite beta, and C opposite our right triangle. Well, if this is a right triangle, we know that the sum of all three angles is always 180, and if one of these angles is a right angle, then that leaves the two acute angles, alpha plus beta, to add up to 90 degrees. And we know that when two angles add to 90 degrees, they are called complementary angles. So if alpha plus beta equals 90, then I could solve this for alpha, and alpha would equal 90 minus beta. And if I come in here, right, and I solve this for beta, then beta would equal 90 degrees minus alpha. So the other thing we know is that from a right triangle, we can find the sine of alpha by taking its opposite side and dividing it by the hypotenuse. So the sine of alpha in this case would equal A over C. If we want to find the cosine of beta, so here's beta, we know that the cosine is found by taking the adjacent side, and the side adjacent to angle beta is side A, and dividing that by the hypotenuse, which is C. So the cosine of beta is also A over C. So if the sine of alpha and the cosine of beta both equal A over C, then the sine of alpha would equal the cosine of beta. And if from here, alpha is the same thing as 90 minus beta, then the sine of 90 minus beta would equal the same thing of the cosine of beta. Right? And if I start from here, if beta is the same thing as 90 minus alpha, then the cosine of beta would equal the same thing as the cosine of 90 minus alpha, and that would be the sine of alpha. So the sine of 90 minus beta is the cosine of beta. The cosine of 90 minus alpha is the sine of alpha. And what we see is that the cosine of an angle is the sine of the complement of that angle. And that's why we call it the cosine. Now, likewise, it would be true that the cotangent of an angle is the tangent of the complement of that angle, and the cosecant of an angle is the secant of the complement of that angle. So from that, we get what we call the cofunction identities. And those cofunction identities say that the cosine is the sine of 90 minus theta, or the cotangent is the tangent of 90 minus theta, or the cosecant is the secant of 90 minus theta. Likewise, the sine is the cosine of 90 minus theta, the tangent is the cotangent of 90 minus theta, and the secant is the cosecant, right, of 90 minus theta. Things to note here, well, and then we have likewise, so this would be for degrees. For radians, right, we have the same relationships except we're using x instead of theta, and we're using pi over 2 instead of 90. Okay, these identities you need to memorize. I want you to make flashcards for these. So label them your cofunction identities, and you should make at least 6 of them, one for each set. Right? You could put both degrees and then radians on the same card if you wanted to. All right, so let's look at using those cofunction identities. So we're going to do what we've done before with trig identities. We just have a new set. So we are given that the sine of x equals 0.3. So that's given information. We're going to come back to that. Our job is to find the cosine of pi over 2 minus x. So that's what we're going to start with. We have the cosine of pi over 2 minus x. Well, we know by our cofunction identity, right, so we're going here to here with our cofunction identity, right, that the cosine of pi over 2 minus x is the same thing as the sine of x. That's our cofunction identity. And we know from this given information that that is equal to 0.3, right? And that's just, right, so we went from here to here just by substitution. And we're done. Let's look at another one. If the tangent of 90 minus theta equals 3, our job is to find the tangent of theta. So again, this is if is given information. Our job is to find the tangent of theta. So we're going to start with the tangent of theta. Right? Well, what do we know about the tangent of theta? By our cofunction identity, right? So by our cofunction identity, we know that the tangent of theta is the same thing as the cotangent of 90 minus theta. That gets me this expression, which I'm looking for. Now, what do I know about the cotangent? Well, I know by my reciprocal identity that the cotangent of 90 minus theta would be the same thing as 1 over the tangent of 90 minus theta. Now, I know what that tangent of 90 minus theta equals, so by substitution, I now have 1 over 3, right? And I have evaluated what the tangent of theta equals. Okay, not too hard. Let's look at another one. Okay, here I'm trying to simplify, right? So I want to do all the math I can and make this expression as simple as possible. The cotangent of theta, right, over the sine of 90 minus theta. So we're going to start with that. I have the cotangent of theta over the sine of 90 minus theta. So the first thing I'm going to do is I'm going to apply my cofunction identity to the sine of 90 minus theta, and I have my cotangent of theta on top over the sine of 90 minus theta, which is the same thing as the cosine of theta. Now, I'm going to go from there and I'm going to use my definition of division, and I'm going to rewrite this as the cotangent of theta times 1 over the cosine of theta. And then I'm going to use my quotient identity. So I'm going to use my quotient identity to rewrite my cotangent as my cosine of theta over the sine of theta times my 1 over cosine of theta. My cosine of thetas will divide out. That leaves me with 1 over the sine of theta. And we know by our reciprocal identities that 1 over the sine of theta is the same thing as the cosecant of theta. And this expression, right, looks a lot simpler. There's a lot less ink involved in order to write that. So we're going to call that simplified. I don't know that there's an easier way to write that expression. Okay? All right, now we're going to verify the identity. So we know that when we verify or prove an identity, we only work with one side, and we usually want to pick the more complicated side. I would say that this left side is more complicated. So we're going to start with the cosecant of x times the sine of pi over 2 minus x equals cotangent of x. So I think the first thing I'm going to do is I'm going to rewrite this sine of x using its cofunction identity. So the sine of pi over 2 minus x is the same thing as the cosine of x. That's my cofunction identity that goes from here to here. And then I'm going to multiply that by my cosecant of x. Well, I'm pretty sure my reciprocal identity for cosecant of x is 1 over the sine of x. Right? That's my reciprocal identity. So now we multiply those two fractions and we get cosine of x over sine of x. Aha! Looking for cotangent of x by our quotient identity, that equals the cotangent of x. So we've worked with that left side until it looks just like the right side. We have proven that identity. Cooking with gas. Okay, so those are our cofunction identities, simplifying, evaluating, solving. Actually, we didn't solve, but proving identities with them. We're going to look at another set now, which are called the odd-even identities. So the definition of an even function. So f of x is an even function if we can input a negative x for x, and the result of that is exactly what f of x would give us. Okay, so here's an example. We have this function y equals x squared. So I'm going to use that here. And if f of x equals x squared, then if I find and evaluate f of the opposite of x, then this function rule tells me that I'm going to take my input and square it. So I'm going to put in that negative x. And we know that if we square a negative, it's like multiplying negative 1 times negative 1, it becomes a positive, and we end up with x squared. Right? So f of negative x ends up being x squared, which is exactly what f of x is. So because these two are the same, right, we have shown that y equals x squared is an even function. Okay, one thing that's true of an even function is that if an even function contains the point xy, then changing x to its opposite will not change the output. So it will always also contain the point negative xy. So if y equals x squared, we know that 1 squared is 1, and negative 1 squared is 1. So you can see that the opposite x's give you the same y's. That function would also contain the point 2, 4, because 2 squared of 4 is 4, and negative 2, 4, because negative 2 squared is 4, right? Likewise, it would contain the points 3, 9, and negative 3, 9. So if I graph this function, we know that it would contain the point 1, 1, and negative 1, 1. It would contain the points 2, 4, and negative 2, 4, and 3, 9, and negative 3, 9. Right, would contain the point 0, 0, and I get a graph that looks like this. Okay. That graph is symmetric about the y-axis. If we fold this graph along this y-axis, right, what's on one side would fold right on top of the other side. So we have this idea of symmetry across the y-axis for an even function. So let's talk about which trig functions are even. Let's see. If we look at the graph of y equals the cosine of theta, actually let's make that the cosine of x, we know the graph of the cosine looks like this. Right? This is at 0, this is at 2 pi, this is at negative 2 pi, reaches a low at negative pi and at pi. That graph is symmetric across the y-axis, so y equals the cosine of x is even. If we look at its reciprocal function, y equals the secant of x, that graph, right, looks like this. You've got a vertical asymptote, and then it looks like this, another vertical asymptote, and it would have, right, another curved section, and so on. That function is symmetric, even. Mirror image across the y-axis. Y equals the secant is an even function. Let's talk about odd functions. So the definition of an odd function is that f of x is odd if when we substitute negative x for x, we actually end up with the opposite of what we get when we plug in x. So here's an example, y equals x cubed. Let's look at this definition, right? F of x is x cubed. If we take our function and we substitute negative x where x is, then we end up with, right, using negative x as our input, negative x, which we will cube. Well, when we cube a negative, that's like taking negative 1 times negative 1 times negative 1. The result is negative x cubed. And what we end up with when we put in a negative x is the opposite of what we put in, what we get when we put x. That shows that it's odd. And as such, if an odd function contains the point xy, it will also contain the point negative x, negative y. The opposite x produces the opposite y. If we look at the graph then of y equals x cubed, it's going to contain the point 1, 1, and negative 1, negative 1. It would contain the point 2, 8, and negative 2, negative 8, and so on. And the graph of that function would look like that. Right? This graph mirrors itself, right? But it's not across a single axis. It's almost as though I'm taking one side, so in this case the right side, and then if I flip that over the y-axis, I get that piece, and then if I take that and flip that over the x-axis, then it falls right on top of here. When that happens, we have what we call symmetry about the origin. It flips over both the x-axis and then the y-axis, and that is true of all odd functions. So, which of our trig functions are odd functions? Well, we have one trig graph that looks like this. And if you think about that, if you take this section, if you take this section here, flip that over the y-axis, and then take that and flip that over the x-axis, right? Then what's on the right side of the y-axis flips over the origin. So this is the graph of y equals the sine of theta, or sine of x, and it is an odd function. Likewise, its reciprocal, which would look like this, right? That's y equals the cosecant of theta. Also, right, you can see the reflection from the upper right-hand corner to the lower left, so that flips over the x and then over the y. That cosecant function is an odd function. Let's look at the tangent. The graph of the tangent looks like this, a vertical asymptote, and so on. Right? And we see that symmetry about the origin again, right? Flip here, it would fall on top of itself. And if we look at the cotangent of x, its graph looks like this. Right? Vertical asymptote here. And if we were to take, say, this piece right here, flip it over here, and then flip that over the x-axis, it would fall right here. Okay? So we have two functions that are even, cosine and secant, and 4 that are odd. That leads us to our odd-even identities. Those functions that are even, right? What's true about them is that the cosine of the opposite of x will give us the same thing as the cosine of x, and the secant of negative x will equal the secant of x. And for our odd functions, when we replace the input with a negative, we get the opposite of what we get with the positive. So that would be true for sine, cosecant, and tangent. And you need to make flashcards for these identities. So you need to memorize these identities, be able to use them. So let's look at using them, and we're going to verify this identity. So I'm going to verify that the secant of negative x over the cosecant of negative x equals negative tangent of x. So we're going to start with this secant of x. Secant of x is even. So as such, the secant of negative x is the same thing as the secant of x. Cosecant is 1 over sine. That's odd. So the cosecant of negative x is the same thing as the opposite of the cosecant of x. So I have applied, right, to go from here to here. I used my odd-even identities. Now, I want to get this to negative tangent. So we have some options here. Actually, we're there, aren't we? By our quotient identity, right? So by our quotient identities, isn't secant divided by cosecant tangent? And so with our negative, right, that can be brought out in front, and we get the negative tangent of x. And we're done, right? We have proven that identity. All right, let's get another one. Here we have the sine of theta minus 90 equals negative cosine of theta. Okay, here's my problem, and that's that this looks like my cofunction identity, but the order of these are changed, right? And one thing you might remember is that we can't change the order of subtraction, but what we can do is change it if we flip out a negative. So a minus b is the same thing as the opposite of b minus a. So if I apply that principle to the sine of theta minus 90, so right, what I'm really doing is I'm factoring out a negative 1, then I end up with the sine of the opposite of 90 minus theta. Okay? So that's just taking the negative 1 so I can flip this subtraction around. Now, that leaves a negative in front of my input. So think of this like my x, and I have the sine of negative x. Because the sine is an odd function, we know the sine of the negative of something is the same thing as the opposite of the sine of the positive, right, of what we have the negative of. So of the positive of 90 minus theta. Okay, now we can apply our cofunction identity, and right, so from here to here we're going to use our cofunction identity, and we have this opposite. We have this opposite, and we know the sine of 90 minus theta is the same thing as the cosine of theta, and that's what the other side equaled. Okay, so let's just recap there. When we had theta minus 90 instead of 90 minus theta, we factored a negative out of the theta minus 90, which gave me the 90 minus theta, which is the order I wanted for cofunction. But I had this negative inside the sign, so I used my odd identity and applied that the sine of the negative of something is the opposite of the sine of its positive, and then I proceeded from there. Okay, blank page, I guess that's it. So you've got some flashcards to make from these, and we will work on these problems tomorrow. No Google form for tonight, just you've got your notes in there. So thank you for listening. We will see you tomorrow.